Okay, we're going to have a little bit of fun today. So this is probably the last problem in this series, although there are other combined load problems that I've posted, which give great practice, great review. This is the last one where I'm trying to kind of evoke a way of thinking. Now I'm going to do something a little bit different with this. In that we're going to create the graphs for the various forces in the X, Y, Z directions and the moments about X, Y, and Z. And we're going to lay them out on the structure itself. Now, I'm going to do that in the global coordinate system, which is to say, the force in the Z is going to be an axial force on one component, but it's going to be a shear force on another component. And I want to do that so that we can look at how those forces, calculable in absolute coordinates, vary in how they affect the member that they're being graphed on. Now, normally when we would graph this with a computer program or something like that, and quite often I would say it's very typical that we would put them into what we call local coordinate system, as in for each of the structural elements, they would be in their local XYZ coordinate system so that you know exactly how they're affecting the member. But I'm not going to do it this way because I want to get you to think about how the structure in 3 dimensions really is impacted by the orientation of the force relative to the member. So we've got basically an angle, if you will, cantilevered out from the wall. So it's going out 5 meters, and then it's got a right angle, an abrupt right angle, and it goes off in the, the positive X direction, 2 meters. It's got a triangular distributed load on that arm, and it's got a point load at the end at point C. And ultimately what we want to do is we want to look at a cross-section 1 meter from the support, and we see where point D is located kind of on a 45-degree angle up. And that just kind of makes it all interesting because it makes every calculation a little bit tough. So I've gone ahead and done the section properties. I calculated the area. I did the moment of inertia about, it would be bending either about the X, the Y axis. Indeed, it would be even bending about the Z axis if you're talking about the component BC. So that's calculated out. I calculated out the polar moment of inertia. That would be the same for all of the section, regardless of where it is. And then I did Q, and I did Q for where point D is. Of course, Q varies over in the cross section, depending on where you are, a distance up or down from the neutral axis. And so that's calculated there. Now, that can be a little bit complicated, but I'm not going to take the time to go over it because we're going to spend enough time on this problem as it is. But let me scroll down and show you that calculation. It really is just a matter of looking up what the area of the shaded area is and where its centroid is, and then you can do the calculation. But I'll just move this up so you can see it. So that's where I did that calculation. I looked up some values in some textbooks and whatnot. And so I just drop it here for a brief moment. You can take a screenshot of it if you will. If you want to go back and make sure that you can actually do that calculation, might be worthwhile. To be fair, it's if you understand the theory and you can go and look up the essential information in a textbook, it's not that hard. But otherwise, I'm going to get back to the problem and otherwise assume that we're okay with Q as calculated. Okay, so here we are, and the process that I'm going to do here is I'm going to calculate all of my reactions at the fixed end, or at point A. And so because it's fixed and we're dealing in 3 dimensions, there's 3 translations, if you will. So forces in the X direction, the Y direction, and the Z direction, all at A, as well as 3 potential moments with moments about X, moments about Y, and moments about Z. And so I'm going to calculate each of those, and then from that, we're going to draw the graph or the diagram for the forces, the shear forces, and the moments that are appropriate to what we're doing. And so let's get on about it. Let's do the reactions. So my first reaction then, I'm going to start with sum of the forces in the y direction is equal to 0. And so we have our RAY. So I've drawn all of my reactions in as positive just to make it simple. And then if I get a negative sign, I'll just deal with it as a negative. And so then my triangular distributed load is acting in the positive y direction because y is shown as positive down. So that's equal to 1/2 times 5 kilonewtons per meter times its base of 2 meters. And so that gives us an RAY equal to -5 kilonewtons. And I'm just going to right away go up, find my RAY, and put -5 kilonewtons in for RAY. Okay, just keep on going. So sum of the forces in the z direction is equal to 0. And so what do we have? We have our reaction in z, again positive, and our 10 kilonewton point load at C is acting in the positive z direction, so plus 10 kilonewtons. And so we get RAZ equals -10 kilonewtons. And so we have one more force, and so that would be sum of the forces in the x direction is equal to 0, and we get RAX, and we have no other forces acting in the x direction, so we know RAX is equal to 0. I'm just going to write it down over here just so that they're all lined up, and I'm going to add them over here. So that's equal to 0, and our RAZ we had was -10 kilonewtons. Okay, so now we have 3 of our possible reactions, so we want to get the other 3. They're all moments, so we're going to be doing the sum of the moments. Now I'm going to assume positive using our positive about the axis that we're dealing with using the right-hand rule. So I'm not going to write down, clockwise and everything else because it gets too complicated in 3 dimensions. So let me get the right color pen. Sum of the moments, and I'll do some of the moments about A in the x direction. Of course, you have to do it about a point. Is equal to 0, and so that's equal to our MAX, which of course we wrote them all in as positive. And then if we use our right-hand rule, we see that the triangular distributed load is trying to turn it negative. So that's -1/2 times 5 kilonewtons per meter times 2 meters, and it has a perpendicular distance to it of the 5 meters, which is the length between A and B. And so we get MAX is equal to 25 kilonewton meters. Now we do sum of the moments. Again, we'll do about A, and we'll use the y-axis is equal to 0, and so we can put in MAY. Again, we drew them all in as positive, and if I look at the 10 kilonewtons, it's trying to go negative, and so we have -10 kilonewtons multiplied by its perpendicular distance, which is the 2 meter length BC. And so we get MAY is equal to 20 kilonewton meters. And finally our last one. So sum of the moments at A in the Z is equal to 0, is equal to our MAZ. And what do we have? So our triangular distributed load is trying to turn it positive, what it said. So that's 1/2 times 5 kilonewtons per meter times 2 meters times its moment arm, which would be 2/3 of 2 meters. And that gives us an MAZ is equal to negative 6.7 kilonewton meters. Now I'm just going to tidy this up a little bit so that they all line up. There we go, little tidier. And so we have all our reactions. So let's get those moments put in up here. So we have MAZ is equal to negative 6.7 kilonewton meters. MAY is 20 kilonewton meters. And MAX is 25 kilonewton meters. So we have our free body diagram completely annotated and what those values are. And so before we get on to calculating our stresses at D, what I want to do is spend some time and see if I can build these diagrams. Again, a little bit strange in that I'm doing them all in the global coordinate system, but it's going to hopefully excite your interest as far as how everything transitions from one member to the other. And so the first one I want to do, and notice I didn't call it an axial force diagram because it may be axial in one component of the structure and something else in the other component of the structure. So the first thing I want to do is to do my force in the Z direction. And if I look at my structure, that force in the Z direction would be an axial force between A and B, and at the cross-section where D is, the area of interest. But then it would be a shear force between C and B, but it's still the force in the Z direction. And that's why I labeled it the force in Z slash the shear force in Z, because it depends on where you are in the structure. So if I look at the reaction at A in the Z direction, it's going to the left 10 kilonewtons or negative 10 kilonewtons. And so if I do my method of sections, that means on that positive face, it's going to be going to the right or in a positive direction. So I'm going to draw this. So we'll go up to 10 kilonewtons. And it doesn't change between A and B, so I'm just going to draw it as a constant value of 10. And at that point in time, of course, it's going to continue between C and B because it doesn't return to 0, but it transitions from being an axial force to being a shear force, but it still has to get out to where that point load is going to bring it back to 0. And so we get back here, and then it goes back to 0. And I'm just going to note that, this is an axial force in here, and to be fair, it's axial tension, whereas this is a shear in that direction. Now, we're not actually calculating anything out at CB. It's not our area of interest in this problem, but it is worth noting how that changes because these are all drawn in the global coordinate system. So I'm going to go down and I'm going to do the force in the Y direction right now. And so the force in the Y direction, so we have RAY, which is negative 5 kilonewtons, which means it's going to be going up 5 kilonewtons on the positive face. Now, typically, if I'm doing straight up shear force diagrams, stuff like that, I would going up would be a negative for us. But I'm going to just try to be consistent to the global coordinate system. And then when we do our stresses, we're just going to have to interpret that a little bit. And so I'm going to go up to 5 kilonewtons. And then there are no forces between A and B. So having arrived there, of course, as we turn the corner and go between B and C, the triangular distributed load, which is ultimately what caused this, is now going to start to reduce it to zero, and it will do it at an increasing rate, so that linear relationship between B and C on the load intensity diagram becomes parabolic as we connect up to our diagram there. And so we can draw that in. And so we have a constant 5 along A to B, and then reduces in that format back down to A. So I'm going to move up my diagrams here. Hopefully we can still keep track of what's going on. We don't want to get too far from our free body diagram. So now we start on our moments. And so the moment about the x direction, we have a positive 25 kilonewtons for our reaction, and that's going to cause a negative 25 kilonewton meters on our positive face if we did our method of sections. So I'm going to just draw this down here, and we'll start at minus 25. Again, we're going to have to use a little bit of interpretation as we go through. And so that's going to vary linearly because the moment arm is decreasing until it gets to a value of 0 when we get to point B. And so I'm going to draw that in as a linear line as it gets to 0 out here. And then it doesn't continue between B and C. It just stays at a value of 0. So we're pretty happy with that. And now we're going to have to look at the moment about the z-axis. And so it starts at negative 6.7. So again, reversing that for the positive face. And so our moment about z starts at a value of 6.7. So I'm just going to draw it in here. So 6.7. Now, first off, it's going to stay constant as we go between A and B. And so I can draw that in. And if I want to consider what that is, so the m at z along A to B is going to be a torque. So I may as well kind of here. So this is a torque or torsion there. So once we get to B, again, that triangular distributed load is going to start to reduce the moment. And if I were to draw it in here, you're going to have a little bit of a curve to it as we go up here. And so that torque about z between A and B is actually bending when it turns the corner and goes between B and C. So we have one more diagram to do. And again, I'm going to have to push this up a little bit to be able to fit it all in. And in this case, we're talking about the moment about the y-axis. And so the y-axis is going down. So again, we look at m at y, and our moment at A of y is 20 kilonewton meters. So we're going to flip that in as a negative 20. And then it goes constant because there's no forces applied between A and B. And it goes out there. And then this is as a result of that point load. So it is going to vary linearly back to 0 between B and C. And so where this is bending in here, and we look, so this is bending about the y-axis, which is the vertical axis. And so if we're bending about the vertical axis between B and C, it is also bending out here. And the moment x would have been torsion between B and C, but it's got a value of 0, so we're not really worried about it. And so that's our graph. It's not quite as clean as when we're working in 2 dimensions or in local coordinate systems where we can call them axial force or normal force, shear force, and bending moment diagrams, because we're dealing completely in global coordinate system in this way, and that's why I said it's a little bit bizarre. It gives us a good insight as to what's going on, but it breaks down a little bit as far as being directly useful. So it is useful in that when we look at point D, we can draw those values off the graphs, but we're just going to have to interpret a little bit as to what they are and what they're doing. So let's get on with it. Let's go back up. We can come down as required. And now we can start calculating our stresses at D. So we're going to start. We're going to do all of our normal stresses, and then we'll do our shear stresses. And so the first one is as a result of the axial force. And so, that's why we talked about each of these diagrams as we were doing it out. The axial force is a result of P at Z. And so we can see off our graph, and I'll highlight the point here where D is. So it's constant at 10 between A and B. So it's going to be 10 kilonewtons at the cross section where D is. And so for our axial stress, we go sigma is equal to P over A, and that's going to be our 10,000 newtons divided by our area, which is 7,854 millimeters squared, and that gives us a value of 1.27 megapascals. Now I'm just going to, because of the way we've done this, I'm going to use my logic again, just to verify the sense of this stress. Is it tension or is it compression? Now, I drew it on the diagram because we went through the logic when we drew the diagram as tension, but I just want to make sure. So if it's in the positive Z direction, that's going to put this whole thing into tension, and so it's going to be a tensile normal stress. And now we're going to go down, we're going to do our normal flexural stresses, and so we're going to do our stress in the Z direction as a result of bending about the x-axis. So stress in the Z direction, because that's also in the Z direction. All the normal stresses will be in the Z direction at point D. So stress in the Z direction is equal to our moment about the x-axis, and that will vary based on our distance in the y direction, all about our I in the x. So we can figure that out. So let's go down and look at our moment in the x direction. So it's 25 or negative 25 kilonewtons. I'm not going to worry about my sign because I'm going to figure out the sense of it using logic. So it's going to be some value between 25 and 0. So that will vary based on my distance. And so I need to know this value right here. And so if it goes from 25 to 0 and we're 1/5 the way along, so that means that that value is going to be 20 at that point. And so that's the moment that we're going to be interested in at this cross-section of interest. So let's put that in here. So we have 20, actually, kilonewton meters, so 20 times 10 to the 6 Newton millimeters times y, which is our distance to point D from the neutral axis. And so that's 45 degrees up. Did I write that down anywhere? So that is going to be 35.4 millimeters, and that would have been in the cross-sectional properties section down below. So that's a distance of 35.4 millimeters from the neutral axis to point D, divided by our I, which is 4.91 times 10 to the 6 millimeters to the fourth. And let me just calculate that. And we get a value of 144.2 megapascals. And so let's figure out if that's tension or compression. And so we're bending about the x-axis. Our moment on our cross-section is in the negative direction. And so that means we're going to have compression at the bottom, which kind of makes sense. You look at this whole thing, it's going to be bending down under that triangular distributed load and bending away. So in this case, it's bending down. It's going to cause compression on the bottom, which means it's going to cause tension on the top. And that will be a tensile stress. And finally, we have our sigma z as a result of bending about the y-axis. So we have our m at y, and we're going to vary in our distance x, and this will be our I sub y. And so if I go down and look at my m sub y, and that's off the page, so I'll just scroll down a little bit to see what that looks like. And it is constant between A and B and a negative y of 20 kilonewton meters. So let's go back up here. So this is, again, 20 kilonewton meters. Our distance x to d is the same because it's symmetric there, so 35.4 millimeters. And so divided by our I, which again is the same because it's symmetric, times 10 to the 6 millimeters to the fourth, and that's going to be equal to 144.2 megapascals. Now, our m sub y was in the negative direction. On the positive face, it's going to flip to be in the positive direction, which is going to put compression on the back side away from us. Which makes sense with the diagram. The 10 kilonewtons is going to try to bend this away from us. So compression on the backside, which is where D is. So this will be compressive. So now we need to look at our shear stresses. And we've got transverse shear stresses, and we've got shear stresses due to torsion. So as far as transverse shear stresses, we have the one, which is our y direction. And so we're going to have a tau as a result of V in the y direction. So that's VQ over IT for transverse shear stresses, VQ over IT, that's V in the y direction. That'd be Q, I guess it's in the x direction at D. I sub x, and our thickness across that cross-section. And so what do we have? So our V at y is constant, so at the point D is still going to be 5. 5 times 10 to the 3 newtons times our Q, which we calculated at point D, 29.5. times 10 to the fifth, times 10 to the third millimeters cubed, divided by I, which is 4.91 times 10 to the 6 millimeters to the fourth, and a thickness, which we had calculated earlier, 70.71 millimeters, and that was down in the part of that section that I showed you, and that gives us a value of 0.42 megapascals. Now let's look at that. So our reaction AY is going up, which would mean on that positive face it's going down to give it equilibrium, and so let's mark that as down so we get it in the correct direction. Now the last one we need to do is to look at torsion, which of course is our torque or moment about the z-axis on that cross section. And so due to torsion, we get a tau, and that's equal to TR over J, where the torque is the moment about the z direction. And so let's do that out. We have a value of 6.7 times 10 to the 6th newtons, millimeters, times our radius, which is 50 millimeters, all divided by J, which is 9.82 times 10 to the 6th millimeters to the 4th, and that's equal to 34.11 megapascals. And that, if I look at the M and Z was positive going out, so that's going to be up and right. And there we have all of our components of stress that we have to put on our differential element at D. Now we still have a little bit more of a complication because, as you see, our shear stress due to torsion is, because of the way it's going around, is up and to the right. So we're going to have to convert that to what components are in the x direction, what components are in the y direction. And so we're going to do that. So I think that's probably the next thing we should do is let me draw in a couple diagrams to show that little transformation. And so we're going, here we have it drawn in, and we're going to be looking at the shear stress components, but specifically for the torsion, because they're off angle. And so if I were to draw those in, so we said 34.11 up and to the left, not up and to the right, up and to the left. And so let me draw that in on our angle diagram. So it is doing this, and obviously along that face would be here, and we can imagine it on the other two faces that I don't have drawn. We want to convert that into our global coordinate system so we can add it to or subtract it from the other shear stresses. And so what we need to do is, it's basically on a 45-degree angle, so we're just, cos or sine 45, and we end up getting our values of, so the component that's going to the left then is 24.11, as is our component that is going up, as this would be symmetric transformation, and that would also have a value of 24.11. And so that converts that shear stress due to torsion into x and y components. And so now with that transformation done, they're all can be added together. So let me draw one more box in, similar to what I just drew. So if I were to look at this, now that I have this here, I want to do my normal stresses. They're all in the x direction. So the compression of 144.2 balances out the 144.2 tensile stress, so they just cancel each other out. And so I end up with a 1.27 megapascal tensile stress, so I can draw that in. And that obviously is reflected off the back. I can see that. And so that's 1.27 megapascals. And that leaves us our shear stresses. And so we have 0.42 megapascals down, and that has to be subtracted from the 24.11 going up. And so we end up with 23.7, megapascal shear stress going up. And that would be balanced here. And obviously the 2 on the back face that we're not showing. So that's 23.7 megapascals. And that was equal to our 24.11, subtract our 0.42. And then the one that we have going to the left, the 24.11, is still going to the left, 24.11, because nothing balances or adds or subtracts from it. So we can put that in. And that's our 24.11 megapascals going there. And again, the 2 shear stress components that would be on the other 2 faces that we're just not seeing here. And that brings us to the end of our superposition. So we actually have our stress condition at point D fully defined. Now, I'm not suggesting that this is the way exactly that I would solve this normally, but I thought it was worth going through so that we could see that complexity of 3 dimensions integrating and working together. As you start to go to more complicated structures, you're going to have to flip back and forth between what we call global coordinates and local coordinates, because we would normally do these diagrams in a local coordinate system for the member itself. And that is a little bit easier to understand, but it's important to understand how it behaves on one is different as it turns a corner and works on another element. So I thought it was worth going through and laying it out this way the one time. And again, I wouldn't necessarily suggest that that's how you would do it when you solve it out. Let's see if I can bring the whole thing, get it all on the screen. It's a quite a convoluted little problem that we went through. And again, this was more about getting your mind understanding and comprehending that complex 3-dimensional transition. And it really is a lead-in for the next course or courses that you're going to come up with. But we're going to deal with it in those instances in a more structured and less abstract way, I guess. So you don't have to be bending your mind around corners and everything all the time. So hopefully that was helpful. Like I say, there are a couple more examples already posted on doing combined loads, and they follow a more traditional, this is how I would do it type of pattern. So I do encourage you to continue on looking at some more examples, and I'll put the links up here so you can see them. So again, hopefully that was helpful. A bit of a long problem, but it really culminates a lot of what we've been looking at over the last few months.